function whose growth is proportional to the quantity present. So this is how your bank account behaves. This is how bacteria behave when food and space are plentiful. And in fact, I've been saying bacteria a lot. This is how basically any organism behaves when food and space are plentiful. If resources are not a concern, all living creatures grow exponentially. There's some more interesting models that take limited resources, limited space into account. There's some very interesting differential equation population models that take predator-prey relationships into account. And that would be a multivariable differential equation where you'd be modeling the population of two different species at once over time. So you'd have time as an independent variable, and then the population of a predator and the population of a prey as dependent variables. There's some really interesting stuff you can do with that. I used to live in Michigan, the very, very northern edge of Michigan, where a little ways up into Lake Superior there's an island called Isle Royale. And this island naturally has a lot of moose, a lot of wolves, and 0 humans, which makes it a really, really interesting spot to observe the sort of population fluctuations of this, packs of wolves and herd of moose as they interact. And it's there's some really cool differential equation models you can do with that. I used to work with some mathematicians who worked with that. It was very cool stuff. This is the basic version. The no predators, no prey, no resource limitations at all. This is just grows without bound. So it's not realistic past a certain point, but it makes for good mathematics. I would cut the video here, but it looks like the video already cut for me, so we're already 2.5 minutes into the second part of this, apparently, so I'm just going to keep going. I have very little else that I can contribute at this point in terms of real-world applications. Most of the differential equations that are solved as part of real-world applications are complex enough that they are not separable. So for the rest of this lesson, we're basically just going to be talking about theoretical math stuff. We're just going to make up differential equations and solve them so that we can practice this technique. But if you're very interested in this mathematically and you want to learn more about differential equations and solution techniques and how they're used in the real world, I suggest you take up engineering. Here it pays very well. I hear this from my brother and my father, who are both engineers, and who don't say out loud that they're disappointed in me. But sometimes I suspect that they think it. I'm going to make up another separable differential equation. Let's do y prime equals y times e to the 2. Or let's switch to x's. I want to use x's at this point. Y times e to the x. This will be a good one. So, we know that this is a differential equation because it involves a derivative of an unknown function. Presumably y is some unknown function of x. And when we take a derivative of y, we get the original function multiplied by e to the x. So, we're going to solve this one by separating out the variables. First, we're going to replace y prime with dy dx. and that's going to be equal to y times e to the x. And we're going to get all the y's on the one side and all the x's on the other. As you move these y's and dy's and x's and dx's, as you move them around, please keep in mind the d's have to stay on top. You can't integrate something with a dx in the denominator. That doesn't work. If you're going to integrate some e to the x dx thing, the dx has to be on top. That's why you can't really just divide by dy here. dy is on top. If you divide by it, it'll be on the bottom of this, and we don't want that. We want it to be on top, so it's going to stay right there. It's the dx that's going to have to move. So I'll multiply everything by dx. As long as I'll just do that. So I get dy equals y e to the x dx. And then I can divide everything by y. So that cancels, and I get dy over y equals e to the x dx. This is the separated version of the differential equation I started with. And so now to solve it, I can take the integral of both sides, see what happens. This guy, once again, is going to turn into a natural log because I'm not creative and I failed to make up something more interesting for this second example. So we'll get a natural log of y on one side. Integral of e to the x is an e to the x. I don't need a dx. I do need a plus c, just one plus c. This is an implicit general solution. I'm going to make it an explicit solution by solving for y, by raising both sides for on top of e to the x. So this is going to turn into e to the x plus c. I hope you're a fan of inception. And again, I can do that trick I did with the last one where I sort of bring the c down. I separate this into two things and I bring the c down in front. So we can call this y equals c times e to the x. Again, I have no idea what kind of equation would be modeled, or what kind of phenomenon would be modeled by an equation like this. This is purely an exercise in trying to solve these things. One thing I do want to point out with this and the last solution, though, is this presence of c here. If we're being extremely pedantic, I would have to admit that this, technically speaking, is not a function. This is a family of functions, because c could be anything you want. If c is 1, you get sort of the baseline version of this function. If c is 2, you get something that's twice as tall. If c is -1, you get something that's flipped over the x-axis. C can be anything. So this is an infinite family of solutions. We're going to talk a little bit later about how to solve for c and what happens, what that looks like. And also in what circumstances you do that. But for now, for this problem, this is the general solution. And you're done. So let's do something else. Let's take a quick break from exponentials. Let's see if we can embed ourselves thoroughly into polynomial land. Let's do x squared y prime equals y squared. Well, let's make this a little more interesting. Y squared plus 1. It seems good. Again, no idea what this might model. Also be careful. This is not an exponent, this is a prime. These guys are exponents. So, let's, as usual, start with swapping this y out for or swapping out the y prime for a dy dx. Y squared plus 1. Now we can move around our x's and our y's however we want. Oh, I did this wrong. I was supposed to put the plus 1 on the other piece. Okay, it's fine. No one even saw that. Starting over. Let's see what happens if we do y squared times y prime equals x cubed plus 1. Let's see if this is more interesting. Sorry. This is what I get for not planning these carefully. Y squared times dy dx equals x cubed plus 1. This is still a terrible example. What am I doing? Oh no, this is fine. I just have to multiply both sides of the equation by dx so that it cancels here. And now I get y squared dy equals x cubed plus 1 dx. It's a fairly straightforward separation. And now I can integrate. So here I'll get y cubed over 3 equals x to the 4th over 4 plus x plus c. So this is a implicit general solution, which is not what I want. It's a good step in the right direction, but I want to go a little further. I'm going to multiply everything by 3. So get y cubed equals 3x to the 4th over 4 plus 3x. I'm going to call this c still. If it's an arbitrary constant here, it's 3 times whatever that arbitrary constant is down here. It can still just be a c. It's a different c. If this is c1, then this is c2. So it's a different number, but it's still an arbitrary constant. Now I just need to take a cube root, so I can get y by itself. And that will look like y equals the cube root of 3/4 x to the 4th plus 3x plus c2. Not very pretty, but fortunately we don't have to do anything with it. We can just leave it alone as is. And this is the general solution. We still need to talk about solving for c and specific solutions, or particular solutions. I am not going to talk about those right now. I'll save those for another video, because this is already getting pretty long. But there is one other thing that I want to address with this general topic before I shut this video down. That is, some differential equations are not separable. If we continue with the polynomial theme, we might have something like this. X times y prime equals, let's say, x squared y minus 2x. If you have something that looks like this, attempts to separate this are probably going to fail. Changing it just a tiny bit. So here's what would happen if we tried to separate this. We could still do this. X times dy dx equals x squared y minus 2x cubed. We can try to put all the x's over here by dividing by x. We get dy over dx equals x y minus 2x squared, which is fine for now. I can multiply both sides by dx. That'll leave me with just a dy over here equals x y minus 2x squared dx. And here's where we're definitely going to get stuck. There is no way to extract this y from the right side of this equation and leave this with no y's involved. You can extract it from this piece by dividing by y, but then you'd end up with an over y on this other piece, which doesn't help us. If you tried to subtract that out, you'd have to subtract out the entire term and you'd end up with an x over there. The basic rule of this is if you're deciding whether or not something is separable, you pretty much have to use exclusively multiplication and division. You don't get to really add or subtract things from one side or the other. That screws up the dy dx's and it is not going to be integrable when you finish. So you pretty much only ever get to use subtraction or multiplication and division. So if you end up with something that has multiple terms here with a subtraction involved, if you can factor something out, then maybe it's workable. Like if this was just a 1x here, you could factor out the x and then divide by y minus 2. That would be separable, but that's because you're factoring it. You don't get to use addition and subtraction really. I feel like I've done a poor job of explaining this, but this video is really long already, so I feel like any attempts I try to make now to clarify would just turn into weird rambling. So I'm going to cut this one here. Hopefully this made some sense, and then you can ask me questions about it next time I see you. Thanks for watching, bye!